vertical angles. It's a pair of angles that share the same vertex and that's an E, not a C, sorry, are made by two intersecting lines and are across from each other. So essentially, if I draw two intersecting lines, these angles are vertical. So that is a pair, they're always a pair. So these are vertical angles and these are vertical angles. Now, congruent angles are two or more angles that have the same measure. And when we're identifying congruent angles in a picture, we make the congruent angles have the same number of loops. So these are vertical, but they're also congruent because they have the same number of loops. Same here, these are vertical, but this would also symbolize congruent. So we'll get, there is an actual theorem, but vertical angles are congruent. Complementary angles are angles that add up to 90 degrees. Now, they can either be connected like that. So you have two angles that add up to a 90-degree angle. So maybe this is 30 and this is 60. Or they can be out just loose in the world. So, maybe this is 40 and this is 50. But in any case, no matter what their measures are, they'll add up to 90 degrees. Mm-hmm. Supplementary angles add up to 180. And again, they can either be connected, so you have like a straight line with some angle coming. So you have these two angles, so maybe this is 120 and that's 60, they add up to 180. Or you could have angles out in the world, just loose. So if that was 45 and this is 135 or something. The only thing I came up with to remember the difference between complementary and supplementary and how much they add up to, complementary angles add up to a right angle. So if somebody compliments you, they are right. So that might be a way to keep in track that complementary is 90 and then the other one is 180. As best I could do. Alright, so adjacent angles are angles that share a common ray and a common vertex. Basically, it's just any two angles that are stuck together. So this angle is adjacent to this angle. They're just stuck together.
People love having kids.
Linear pair is two supplementary adjacent. Adjacent does not have an S in it. What was I doing?
Yeah, I was wondering what that was.
Just pretend that was not there. Apparently I couldn't spell. Okay, linear pair is two supplementary adjacent angles formed by two intersecting lines. So when we intersect lines, we have vertical angles, but then we also have linear pairs. So if I labeled these angles 1, 2, 3, and 4, angle 1 and angle 2 form a linear pair, right? They make a straight line. So do angle 2 and angle 3. They make a straight line. Angle 3 and angle 4, linear pair, and then angle 1 and angle 4 form a linear pair. So whenever we intersect lines, we get two pair of vertical angles and four linear pairs. And these, because they're supplementary, 1 and 4, like all of these sets, will all add up to 180 degrees each. So angle 1 and angle 2 add up to 180, 2 and 3 add up to 180, 3 and 4, and 4 and 1. And then 1 and 3 are congruent, and 2 and 4 are congruent. An angle bisector is a ray, similar to this up in the top, but it's a special one. It cuts the angle perfectly in half. So if I have some angle and I draw a ray here, that's not good. Here. Well, that's close enough. This angle measure and this angle measure will be the same. So whatever that number is, if it was like 50 and 50, something like that. So it cuts it perfectly in half. Okay, if you remember, the postulates are statements that are just accepted as true. We don't have to prove them. So the angle addition postulate, and this is like the technical definition, but what it says is if I have some angle ABC, so A, B, C, and I stick D somewhere in there, if I make a ray that goes to D, I'm going to number these angles just to make them clearer. This tells me that the measure of angle 1, that's this angle, this top angle, plus the measure of angle 2, that's the bottom angle, will equal the whole thing. So basically, if you have two angles stuck together, they add up to the whole big angle. Makes sense, right? The angle bisector, it tells you that an angle has exactly one bisector. So there's only one line that will cut the angle in half. Again, that makes sense if you think about it. You can only cut something in half at one spot to make it equal. So only one ray cuts angle in half. And then we have the linear pair postulate that says if two angles make a linear pair, they're supplementary. Part of the definition of supplementary was that they add up to 180 degrees. And part of the definition of them being a linear pair was that they were supplementary. That was the definition of a linear pair. So it makes sense that if you define it by saying it's supplementary, then they are supplementary. And then the linear pair theorem says that if you have a linear pair, they add up to 180 degrees. Well, if they're supplementary, they're 180 degrees. Make sense? So the fact that they are supplementary means that they have to be 180 degrees. So these two things go together. And then the vertical angle theorem says that if two angles are vertical, then they are congruent. So we had already drawn this. If I have vertical angles, this angle has the same measure as that angle, and this measure is the same as this measure. And this is a theorem. This is one of those statements that have to be proven, and they prove it using linear pairs. The red and the blue are a linear pair, so they add up to 180, right? So if this was 40 and this was 140, but then this one and this one also add up to 180, so that would make this 40. Since you go around in a circle and they just keep adding up to 180 every two. So that means these would have to be equal, and so would the blue. The red have to be equal, and the blue have to be equal. What we have are some examples of complement and supplement. And if you recall, complement is right. Supplement is 180 degrees. Now, the difference between these two problems, aside from the number of degrees, is this says and this says of. And that will become important. If I'm finding the complement and the supplement, I'm doing two separate problems. One problem is to find the complement, and one problem is to find the supplement. So First, we're going to find the complement. So we subtract. That's 55. So the complement of 35 degrees is 55 because they have to add up to 90.
And you always subtract?
Always subtract. Now, the supplement of 35 needs to add up to 180, so I do 180 minus 35. And I get 145 degrees. So this word "and" tells me I'm doing two problems.
And those are answers?
Those are your answers. The complement is 55 degrees. The supplement is 145 degrees. The difference between these two problems, though, this word "of," this is one compound problem. Anytime you have complement of the supplement or supplement of the complement, it's a compound problem. So what I need to do is find this part first. And then I take the answer from this part.
So you find the supplement first?
And then I take the answer from this part, and then I find the complement of that. Because I'm trying to find the complement of the supplement. So first I have to find the supplement, and then I find the complement. So I do the second half first, and then the first half second. If that makes sense. So I want to find the supplement of 126, so I do 180 minus 126. So that's 54. And then I take this 54 and I find the complement of it. So the complement of 54 is 90 minus 54. So it's going to be 36 degrees. So my final answer is 36 degrees. And it could say find the complement of the supplement like this, or it might say find the supplement of the complement. Technically, doesn't come up much, but you could even say find the complement of the complement. Would just undo each other though.
So you do whatever one has a number first?
Yeah. So this, two separate problems, because you're finding and means two things, right? This is of, so you find this one first, and then that. Not too bad, I hope. Right, when we have two intersecting lines, that's what we have. We have vertical angles and we have linear pairs. So what I know from vertical angles is that these two are going to be the same and that these two are going to be the same. And I'm going to use that information as well as the fact that the red plus the blue are going to equal 180 degrees. Right? So every red and blue makes a straight line, so those will equal 180 degrees, and the reds are equal, and the blues are equal. So if I look at the blues first, like X, because normally you think X first, but if I look at the X's, there's no measure over here, so I can't do anything with that. So I need to go to the Y first. And I can tell you that Y is equal to 123 degrees because these two angles are the same. Degrees. And X plus 123 degrees, these two together would equal 180. So I need to do 180 minus 123. That's what X will equal.
How does X equal 180?
See, this is, yeah, we have the straight line. So this straight line, all total is 180, and these two angles together will make up that 180. So 57 degrees. So anytime you see the two intersecting lines, you're going to be working with vertical angles, linear pairs, things like that. With D, we've got one line this way, one here, and one here. And so what that tells me is that if I look at the green and the blue, these are vertical angles. And then from the green and the blue, X would be equivalent to, wait, sorry, X is yellow and blue, so it would be equivalent to all of this.
How's X 47 on C?
90 minus 43. Okay. So then my other set of congruent angles come from the green and the yellow. So this angle and this angle are the same. Now, I can't find X yet because I don't know what, I know this is 36, but I have no idea what that is. This is 27. Not that I'm being asked for that, but I'm just going to write it down because I know what it is, and that gives me just one more piece of information. Now, Y and 36 have this right angle, so I know that those are going to add up to 90, so Y is 90 minus 36. So that's 54. Okay, so if this is 54, that makes this 54. I still don't know what that is, so it's not going to be useful. However, this green line is made up of all three of these angles. So to find X, I can use the fact that this straight line is 180 degrees. Instead of a linear pair, I actually have a linear triple. So three angles make up that straight line. So what I have is 54 plus X plus that 27 would equal 180. Did you guys see that? So to find X, I would do 180 minus 57 minus, sorry, not 57, 54. Minus 27. Okay. And so, through the magic, if I already did it, when you do that subtraction, you get 99 degrees. This is called like logical reasoning or deductive reasoning, and it uses conditional statements. Conditional statements are if-then statements. So it's if this, then that. And they usually imply a cause and effect relationship. Your parents have used these forever, and your boss. If you clean your room, you will get allowance. If you do this project, you will get a promotion, things like that. So they're usually written as if-then. They're not always in the form of if-then, but that's the normal state. And they're not always true. They can be true, but they're not always true. So what we have is an example of a conditional statement might be, if you study, then you will pass the test.
Write it down.
Yeah. Okay, so this is a conditional statement. If you study, then you will pass the test. hypothesis is an unproven theory, or it can be a proposition. A proposition like, if you clean your room, then you go out. You know, it's a proposition like, I'm asking you to clean your room. Or it could be a supposition, which is sort of like a guess, or a, well, if this happens, then that probably will happen. So that is the if part of the conditional statement. So in our example, our hypothesis is you study. That's the if part. And the theory is that you're going to study, or the supposition is that you're going to study. Now the conclusion is the last step in a reasoning process. So an entire reasoning process may have more than 2 steps. But in a if-then statement or conditional statement, the conclusion is the then part. So our conclusion is you will pass the test. So our hypothesis is that you study, and our conclusion is that you pass the test. Now remember I said that they may not be true. Conditional statements can be true, but they may not always be true. A counterexample is an example that shows that the conditional statement was false. And usually in order to prove a counterexample or to show a counterexample, it's the conclusion that you're disproving, not the hypothesis. So for a conditional statement to be false, the hypothesis is true, but the conclusion doesn't happen. So if I told you if you clean your room, I'll give you allowance. You clean your room, and then I go, ha, just kidding. No money for you. Well, for us, our counterexample is you studied. So you did study, but you did not pass the test. If you find one case that proves the conditional statement false, just one. So if in the history of human existence there was somebody that studied but did not pass the test, then that entire statement is false. It can never be true. If we find one counterexample, this is a false statement now. Now there are people that might study and pass the test, but this is not a true statement. A true statement is true 100% of the time. Okay, so there are 3 things that change a conditional statement and then 1 that combines. So we have converse, inverse. I wrote this wrong. That shouldn't say converse again, I'm sorry. That's a typo. Cross that out. I apologize.
They all say that.
Yeah, I know, we need to fix it. It's not a this is a converse, this is a contrapositive. So I apologize, I started typing and kept going or something. So you have the converse, the inverse, and the contrapositive. And what these do is they take a conditional statement and they change it. So a converse switches the order. So when we talked about, you know, if you clean your room, then you'll get allowance. It would then be, if you get allowance, then you cleaned your room. It switches it just changes the order of what comes first and what comes second. So I have an example for you. And our example of a converse is if a triangle, oops, sorry, let me do this first. Our conditional so our conditional statement was if a triangle has two congruent sides, it is, wait, then it is, sorry. Then it is isosceles. I just spelled that wrong. I can never spell isosceles, I swear. I-S-O-S-C-E-L-E-S, isosceles, okay. So our conditional is if a triangle has two congruent sides, then it is isosceles. So the converse switches the hypothesis and the conclusion, and so it's if a triangle is isosceles, then it has two congruent sides. Okay, and on the previous page I had written flipped. So converse flips the hypothesis and the conclusion. It just flips it. And sorry about the typo here. We're going to change that to contrapositive. Okay. Biconditional happens when you have a true conditional, so there are no counterexamples, and then you have a converse that is also true. Now if we look at our triangle example, our conditional is if a triangle has two congruent sides, then it is isosceles. This is true. That's the definition of isosceles. So our converse, if a triangle is isosceles, then it has two congruent sides. That's also true. If both statements are true, the conditional and the flipped, so going forward and going backwards, are both true, then you can have a biconditional, which is an if and only if statement. So that would be if, sorry, not if. A triangle is isosceles if and only if it has two congruent sides. And now an abbreviation for if and only if, so that you don't have to write it out every time, is instead of this right here, I could have just put IFF. IFF stands for if and only if in math. So you could have written a triangle is isosceles, IFF. It has two congruent sides. Biconditionals, they're always true. And the reason they're always true, the reason they're always true is because the two statements that made them going back and forth were both true. So biconditional is always true. So if you see any statement that says something if and only if something else, then you know for a fact it's automatically true. You don't have to question it. Okay, the inverse stays in the same order as the conditional, but instead of if A then B or if P then Q, you negate it. So if not P then not Q. Like if you don't clean your room, then you won't get allowance. For our triangle statement, we would say, if a triangle does not have two congruent sides, then it is not isosceles. Okay. An inverse has the same truth value as the conditional. So if the conditional was true, which in our case it is, if a triangle has two congruent sides, it's isosceles, then the inverse is always true. Okay. So we have so far is we have a conditional, and then we can flip it, or we can negate it. And last, we have the contrapositive. And the contrapositive is when you take the inverse, so you've got them both negative, and then you flip them. So we had flipped, negated, both. So if you flip it and negate it, it's a contrapositive. So for our example, if our inverse was if a triangle does not have two congruent sides, then it is not isosceles. We've got if a triangle is not isosceles, then it does not have two congruent sides. Said could or can or cannot be true. First, we want to identify the hypothesis and the conclusion. So, hypothesis. Conclusion. Is it true? Well, what if she did all her homework and she failed? So the hypothesis is true, she does all her homework, but then she doesn't get an A in the class. I guess she didn't even have to fail. What if she does all her homework, but then she gets a B in the class? It's still not a true conclusion, so that would be a counterexample. So here, she fails her test, and so this is one counterexample. She got a B in the class would be another counterexample. She got a C in the class. She got a D in the class. You know, I mean, there's a bunch of counterexamples. So this is not going to be a true statement. We're still on the Marina. Marina does all her homework, then she will get an A in the class. So our converse flips. So if Marina gets an A in the class, then she has done all her homework. Okay, so that's our converse, we flipped. Okay, so flip, negate, both. So our inverse, if Marina does not do all her homework, then she will not get an A in the class. And this one almost sounds like it would be true. But the inverse is always going to have the same truth as the original statement, the original conditional. And if you think about it, there's a chance that, okay, it says all over homework. If she maybe misses one assignment, she can still get an A. So this would still be, this would also be false. And then the contrapositive is where you do both flip and negate. So if Marina does not get an A, then she did not do her homework. Again, I can think of a chance that this might, maybe she didn't get, she did all of her homework, but she didn't do well on the test, so she still didn't get an A. You know, so this is also, we can, I mean, none of these are true in this specific instance. My conditional statement. If you are a native Floridian, then you were born in Florida. This is true. Every single person that was born in Florida is considered to be a native Floridian. The converse is where I flip it. So if you were born in Florida, then you are a native Floridian. This is also true. Since both statements are true, the conditional and the converse, or the flipped, I can write a biconditional statement. Biconditional statements only occur if both the conditional and the converse are true. So my biconditional statement you are a native Floridian if and only if you were born in Florida. There's no other way to be a native Floridian. And if you were born in Florida, you're not a native anything else. Well, Native American, but not a native Californian or a native Tennessean, or I can't even think. So biconditional statements are okay. The properties of equality tell me if A equals B, then I can add the same thing to both sides. So if x minus 3 equals 5, I can add 3 to both sides, and x will equal 8. That's what we use this for. Same thing with subtraction. If I subtract the same thing from both sides, I'm not changing the equality either. Multiplication, I can multiply the same thing to both sides. So if x equals 3, then 2x equals 6. And division, if x equals 10, then x over 5 would equal 2. Divide both things by 5. Okay, so these properties just tell us that we can add, subtract, multiply, or divide as long as we do it to both sides. As long as we do it to both sides of the equation, then we haven't done anything illegal. The reflexive property, reflexive is like a reflection. So 3 equals 3. They just have to be identical on both sides. This gets used in proofs a lot because it's a way to introduce new things into your proof. Because you can't introduce something new into the proof without having a property that allows it to be there. So I can be going along in a proof and I need a 3 or something. So then I just say on my next line, 3 equals 3. That's the reflexive property. It allows us to introduce things. The symmetric property is what allows us to rotate things around the equal sign. So if 3 equals x, well then x equals 3. And that just allows us to make things look the way we want them to look. We can flip them around the equal sign. So reflexive has to be identical on each side. Symmetrics allows us to rotate. Transitive allows us to get rid of the middleman. So if A equals B and B equals C, well, A equals C, that allows us essentially to cross out the B and B part, right? So if x equals 5 plus 1 and 5 plus 1 equals 6, well then x equals 6. We can cross out the 5 plus 1s. It just lets us get rid of the middleman. That's what the transitive property does. It allows us to move through other things to get where we want to go. And then substitution. This is a very complicated way of saying if x equals 2, well then 2x is equal to 2 times 2, so that would be 4. If x is 2, I can take x out and put 2 in. Or vice versa, I could take a 2 out and I could put an x in. It just allows me to change things for other things that have the same value. Like when you get 4 quarters for $1, 4 quarters, it's the same amount of money. It doesn't matter which one you have. You still have your dollar. Commutative property. We have the commutative property of addition, and then we have the commutative property of multiplication, but they're both the same. Now, there is no commutative property when it comes to subtraction or division. Because when you add or multiply, the order doesn't matter. 2 plus 3 is the same thing as 3 plus 2. But if you subtract, 2 minus 3 is not the same thing as 3 minus 2. Or same with division. So all this does is tell us that we can change the order. And that can be useful sometimes, because changing the order of problems makes them easier to just quickly do in our head, possibly. Associative property, again, we have addition and multiplication, no subtraction or division. And the associative property just tells us that it doesn't matter which one we do first. So if I have, I'm going to use addition this time, 2 plus 5 plus 9. Well, maybe I want to add the 2 and the 5 first and then add the 9. It doesn't matter. This is 2 plus 14, which gives me 16. This is 7 plus 9, which gives me 16. In this problem, it doesn't really make a difference, but sometimes it makes more sense to move the grouping because it's easier to add things in certain orders. That's what this is for. Or multiplication comes up a lot. If I do 2 times 5 times 13. 5 times 13 I don't maybe necessarily know in my head. But 2 times 5 I definitely know in my head. So 10 times 13 is 130. So that changing the grouping made it easy for me to just go, oh, okay, I can do that really fast. That's what that's for. And then the distributive property just tells me if I have something on the outside of the parentheses, I multiply it in. We use this a lot in algebra. So 2 times the x and then 2 times the 6. That's distribution. Now, if we go backwards, it's also the distributive property. We call it factoring, but the property is still, so if you start here at the 2x plus 12 and then you turn that into 2 times x plus 6, it's still considered distributive property. Goes both ways. You're just distributing out. So like I said, sometimes things are just so that you can introduce them into a proof. They don't really serve any other purpose. And that would be the reflexive property. To identify the properties, you look on the 2 sides of the equal and see what's happening. In this case, I have 10 and I have 10. They're identical. Anytime you have a reflection, you have reflexive property. Right. On B, I look at this. Everything's in the same order. The only thing that changed was the parentheses moved. If the parentheses moved and that's all it was, it's associative. Now sometimes the parentheses might move, but it changes the order. So you would have in parentheses still 2 plus 1 out front and then plus 3. That was an order change. So that would have been commutative. So if the order of the numbers is the same and just the parentheses moved, that's associative. Do you want me to write that so you could see what I mean? Yeah. If it was 3 plus 2 plus 1 is equal to 2 plus 1 plus 3. So it looks like parentheses moved, but really the order changed. That would be commutative. Here we have a switch of order, so that's commutative. One equals 5 minus 4, and 5 minus 4 equals 2 minus 1. 1 equals 2 minus 1, so essentially this was crossed out, that middle bit taken out, so then that's transitive. Two x plus 5 equals 27, then 2x equals 22. I subtracted 5 from both sides to get here, so that's subtraction. Deduction versus induction. People always say, oh, Sherlock Holmes, deductive reasoning. No. Anybody familiar with Sherlock Holmes? Watch this show, Sherlock, or anything? No, okay. Sherlock Holmes is the British detective, is amazing, always solves all the crimes. Yeah. Well, people mistakenly, yeah, like the movie, people mistakenly say he's using deductive reasoning. He's actually not. He's actually using inductive reasoning. The difference between the two is deductive reasoning is pretty much mostly what we use in math, and with deductive reasoning is you take a fact, given facts, and then you take a series of other facts, actual facts, and you put those facts together and then you come to a conclusion. With inductive reasoning, you observe things. You observe patterns. Like, so when Sherlock Holmes is solving crimes, he's observing things. Like, he looks at people's hands and see that they have a big callus and ink stains, and he says, oh, you're a writer. Things like that. Inductive reasoning might be that you see somebody come to school every day with a cup of Starbucks. So you would induce that they really like Starbucks coffee. Maybe they don't actually have coffee in that cup. Maybe it's tea. You don't know. But you would make the conclusion that they really like Starbucks coffee just from things that you're visually observing. Deductive reasoning tends to be a little bit more accurate, but that doesn't mean inductive reasoning is not accurate. It's just like I said with Starbucks, maybe you think they're having coffee in their cup, but really it's tea. So it's not always 100%. Deductive reasoning may not always be 100%, but you get closer because you're building on facts. We use two-column proofs using deductive reasoning. So we are going to solve equations. Now we can turn this into a proof, but first let's solve it. The first thing I do to solve this equation is I distribute that 3. So I get 3x plus 6 equals 15. Then I subtract 6 from both sides. So I get 3x equals 9. Then I divide both sides by 3, and I get x equals 3. This is my solved equation. Now I can turn a solved equation into a proof where I prove that if 3 times x plus 2 equals 15, then x equals 3. That's a conditional statement, right? I turned it into an if-then statement. And then I can, and then use deduction to prove it. The most visually simple and common proof, especially at this level of math that you'll use, is a two-column proof. One column is labeled statements, the other column is labeled reasons, or you can just put S and R. I know what you mean. We make a list of statements, and then we have to write why they work over here. So the reasons are theorems, postulates, definitions. They things of that nature. So these are going to be theorems, postulates, and definitions. Those are the reasons. Now, if I'm given 3 times x plus 2 equals 15, and I want to prove that x equals 3, I essentially am going to write the same steps as I did in the equation, but all those steps that I had in red, the things I was actually doing, we leave that out. So the first statement in any proof is always what you were given. So you will always get that part of the proof correct. You always write down every bit that you were given. The last statement in every proof, so this is the first statement, this is the last statement. Not 2, I shouldn't say 2. I should say last. So you're trying to get from here to here. So the first thing I did was I distributed it, but I'm not going to actually write in any distribution. I just go to the next step. So that's 3x plus 6 equals 15. And my reason is the distributive property. So we can just write distribution or the distributive property.
What does that say next to prove?
Here?
Yeah.
Last. This statement, this x equals 3, will always be the last. So the given is always the first statement, or statements, because sometimes they give you more than one given. And the prove is always the last thing that you write. Okay. Then I subtracted 6 from both sides, giving me 3x equals 9. And the reason is subtraction. And then I divided 3, giving me the x equals 3, and that was from division. And then the very end of a proof, on this side or towards the middle, you write QED. QED stands for quad erat demonstratum, which is Latin, which means we proved it. It just lets everybody know that, okay, yeah, that you're done. Because some proofs are pages and pages long. So you always write QED at the end that says, okay, finally you're done. You don't have to keep turning pages. You're given the majority of the proof. So we look at, okay, so here's our given statement. And then they added 3 to both sides, so it was addition. And then I have 4x equals 12. To get rid of that 4, I used division. Okay. If we go to B, I was given x equals 4, and I'm trying to prove x plus 2 times x. I'm going backwards, essentially. So they substituted. They took the prove statement, except instead of x's, they put in 4s. So that was substitution. Then they added the 4 plus the 3, so that gave us the addition. Then they multiplied 4 plus 4, or 2 plus 7 to get the 14. So that would be multiplication. Apparently. Okay, and then they added to show that 18 equals 18, which proves that this is true. We won't do a lot of those. Ours will mostly go forward, not backwards. Here we're given the statement. So then what did we do here to get from there to distribution? And then addition. So 16 minus 11 is technically the same thing as 16 plus negative 11, but if you wrote subtraction there, I would not count that off. So it's technically addition, but it's also subtraction, so it's fine. This could be addition or subtraction. To go from here to here, though, That's definitely subtraction. And then division. First statement is always given. So we've got, that was given, and then we added 1 to both sides, and then to get rid of that 2, we multiply.